Today is December 21st, 2022. From my YouTube channel C++ 17 2023 CUDA SQL OpenGL OpenCL TBB Vulkan, click this link. From this playlist, scroll down. Episode 151, How to Implement Numerical Derivatives, 7-point Stencil. From this video, click Show More. Download current video source code. Double click it. Show in folder. Extract. Rename 152. Copy. Paste it in your working folder. In this folder, Mathematical Theory. Copy the folder path. Start Intel compiler CD. We are in this folder, Numerical Derivatives, Mathematical Theory. Open up Visual Studio Code, CPP 17 2023 parallel. From folder 152, Mathematical Theory, derivatives.cpp. Ctrl B. I explained mathematical theory behind numerical derivatives in this video, and we implemented 7-point stencil algorithm in episode 151. In our previous episode, we implemented derivative. When a function f is given, we can evaluate derivative of f. In this case, f is single-valued function. In this section, we evaluate first-order derivative. In this section, we evaluate second-order derivative. This function supports up to 6th-order derivative. We used exception. Now, static assert. We limit order less than or equal to 6. We removed exception. Then we can use no except keyword for performance reason. We will try this function in this function. In the command prompt, dp cpp qsed c++20 ehsc derivatives.cpp or d.exe, hit enter. I will copy this command, Control Home. I will paste it here. Now, CLSD. So, this is the result of numerical derivative. This is the result of algebraic derivative. They should be identical. In this function, function f is sine function. If we differentiate this function with respect to x, it becomes cosine x. Now, if we differentiate sine function 4 times, then it becomes sine function again. So, up to first derivative of sine function works correctly. We take derivative of sine function f. F is sine function. This is algebraic derivative. This is numerical derivative. it works perfectly. Please understand, this is single-valued function. I tested using sine function. The reason I used sine or cosine functions is that any function that has periodicity can be represented as the sum of sine and or cosine functions. That is Fourier series. That's why I tested using sine or cosine function. Now we want to extend our numerical derivatives for partial derivatives. For the test partial derivatives, copy this function name, paste it here. I will disable this function. Now we define order f, order x, order y, order z. So this is three-valued function. Of course, we can add s or t, but for the time being, we will test with three-valued function. Return SED sine x times SED cosine y times z times z. I created arbitrary function. I will copy this, paste. We differentiate with respect to x. Then it becomes cosine x. It is partial derivative. Copy, paste. Now we differentiate with respect to y. Then it becomes sine y negative. Copy this, paste. Now we differentiate with z. Then it becomes z times 2. So these are algebraic derivatives. Now order CMD dx dy dz. We will create command by passing dx1 dy1 dz1. Of course, we haven't created this function yet. Order n fxyz partial derivative. We pass this command. I will say like this. Copy this command, paste it here. We pass this function f here. F is a function with three variable arguments. I will pass arbitrary value. Okay, so this is x, y, z respectively. Now order a f xyz, we can call this function by passing the same arguments. So this is numerical differentiation. This is algebraic differentiation. We haven't implemented this function yet. SED, cout, numerical differentiation fxyz and fxyz, cpz, and L, copy, paste, and L, this is algebraic differentiation. Now I will comment out this part for the time being. We need to create command function first. Scroll up. Here I create a simple function template or n or var index or order. Context for SED size t get SED index sequence. We pass var index order. We can use no except if context for n equals 0, we can return var index. Else if context for n equals 1, we return order. Else return SED size t -1. Okay, this is variable index. It can be x, y, or z. This is order of derivative. Order of derivative, such as 1, 2, 3, 4, etc. For our purpose, this function is good enough. Okay, but I can use more generic algorithm for future use. Template or n or index or indices. This is more generic function. Context for SED size t get SED index sequence. Index indices. No except. Now we have to use recursion. If context for n is 0, return index. Else if context for n is not 0 and the size of indices is not 0, then return. We call this function recursively. Now we decrement to 1 from n, then we consumed the first index. We already consumed this index. So these are the remainders. Copy, paste. We already consumed index. It is type. We have to pass instance. Else, return std sin t -1. This function is generic implementation of this function. Okay. Now here context for auto dx1 std index sequence 0 1 copy. It should be instance. Copy, paste, paste, paste. It can be 2, 3, 4, 5, 6. 5, 6. So it is 2, 3, 4, 5, 6. We can add more. Now copy, paste. It should be dy, y, 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 y. In case of y, it should be 1, 1, 1, 1, 1, 1. Now copy, paste. This is d, z, 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 z. This should be 2, 2, 2, 2, 2, 2. We defined dx1, dx2, dx3. It means differentiate with respect to x, in this case 0. Third order derivative. Of course, partial derivative. For example, in this case, differentiate with respect to 2. 2 means z. Okay. This is fourth order derivative. Fourth order derivative. You understand what all these things mean. Now here, template, type name, types, struct, type, container. This is type container, struct, template, type name, var, ODRs. It means variable order pairs. Okay, var ODRs, variable order pairs. Context per auto create command. We take var ODR, var ODRs, return. We return an instance of this struct. We pass var ODRs. Don't forget, we have to expand the template parameter pack. It should be an instance. Up to this point, we implemented these constant variables. Also, create command. So, this is now enabled. Please understand that we implemented derivative, this function. This function takes f is a function that takes a single variable x. F is a function that takes a single variable. We want to implement partial derivative that can take multiple variables. For such purpose, we have to fix certain variables like this. Template or var index, type name, func type name, arg, types, or fix variables other than var indexed. Okay, other than variable var indexed, we fix all other variables. We take func type. It can be forwarding reference. We pass func, then arg types args. This function can take variable number of arguments. We fix all other variables. We fix all variables other than var index. Once again, this function can take variable number of arguments. We fix all other variables other than var indexed. We create a single valued function out of multi-variable, I say multi-variable function fnc. For such purpose, or fixed or we will return fixed. Please understand that this function takes a single variable. This function takes a single variable. Now here we will capture as L value reference. Then auto arguments std forward as tuple. This is function. because we captured as L value reference, we can use ARGs like this. Then std get var index. This is tuple. Okay. From this tuple, we update v with v. You can say set var indexed arg out of args to v. So var indexed arg from this args to value v. I say over args to v. Okay. Then return std apply. We pass this function because we captured. Then we pass arguments. Okay. This function creates from func and args that takes a single variable. So we convert multi-variable function to single variable function. Please understand, this implementation does not work, but I will explain why it does not work shortly. Now let's keep going. Template, type name, var odr, type name, fun type, type name, arg types, auto partial derivatives. Then we use type container var order. Okay. Fun type forwarding reference fun arg types args. Please notice, in case of function, we use forward reference. In case of ARG types, we haven't used reference type. This is non-reference type. There is very good reason not using reference type. Now here, context for auto var index from we created this get. Get takes indexed sequence as argument. Okay. In this function, var odr, this is the same type. Okay. So get 0, we pass var odr. This is type. We have to pass instance. Now this is order. Okay. This should be 1. It represents variable x, y, z, etc. It represents first order derivative, second order derivative, third order derivative, etc. The type of VAR ODR is indexed sequence because, now scroll down, when we call partial derivative function, we use dx1, dy1, dz1. See the pop-up window. It is index sequence, index sequence, index sequence. It returns container. Okay? It returns type container. Type container. The return value of create command is type container. This type container is this command. We pass this command to partial derivative here. Now scroll up. We want to do partial derivative. We fix VAR index like this. Auto fixed. We call this function. We pass VAR index. Then we pass func here. Then ARGs. It should be expanded. At this point, fixed is a function with a single variable, that is VAR indexed variable. This is single valued function because here we fixed VAR indexed variable. Okay, so we can do derivative. Now auto arguments std forward as tuple. This is function args. Now auto b std get. We want to get VAR index arguments. From this args, V is VAR indexes variables value. Okay. With this, we can differentiate derivative. The order of derivative is order. Then we can pass fixed with the argument v. Please note, we use derivative. This is defined in our previous video. Here, it takes function with a single variable. Okay, this is order. So we pass here order. This is single variable function. This is single variable. In this case, we are doing partial derivative with respect to var indexed variable. This handles single derivative. We want to generalize it. Template, type name, var odr1, type name, var odr2, type name, sorry, I misspelled, var odrs, then type name, func type, type name, arg, types, auto, partial, derivative. Once again, type, container, we pass var odr1, var odr2, var odrs. It should be expanded. Then func type, forwarding reference, func arg, types, args. Now we can enable this part. So it takes 3 derivatives. We first differentiate with respect to z. We differentiate function f with respect to z, then with respect to y, then with respect to x. Okay, so I will copy this and paste it here. It becomes like this: dx1, dx, dy, then dz. Now we differentiate right hand side first. So auto right derivatives. Then we capture func. Then auto arguments. Okay, we will call this function recursively. Now here, to call this function recursively, we need this. Okay, it should be instance, but we will consume right hand side. Okay, we will consume this or dy1, dz1. We will consume these things: odr2, var odr2, var odrs. We will consume these, so we don't need these things. Okay, then we have to pass function that takes multiple arguments. We have to call this function that takes multiple arguments. So this function takes multiple arguments. We pass this here. Okay, then ARGIS. This is recursive. This function actually has type container one type. In this case, type container takes at least two. So this function call is not this function, but this function. In this case, type container takes one type ODR, one type VAR ODR. In this case, type container takes one type VAR ODR1. So this function calls this function. Now here we return this function recursively. Now we will consume VAR ODR1 here. We have to consume dy dz. So copy paste. We will consume VAR ODR1 here. We remove. It should be instance. Now we get this function here. We pass a function. Func takes multiple arguments. We should not pass args, but we have to pass arguments. It should be expanded. Okay, we are creating a new function. In this case, if this is 0, the size of VAR ODR is 0, this function calls this function because it takes one type VAR ODRs. If the count of VAR ODRs is not 0, then it calls recursively. In this case, it takes one VAR ODR, so one VAR ODR equals this function. In this case, if VAR ODRs, the count of VAR ODRs is 0, then this function call goes to here. Otherwise, it calls recursively. Okay, we have to return. Okay, it will not work. It will not work because of this function. I said I made error intentionally in this function. Now scroll down. I will enable. Don't worry about the squiggle yet. Now we will rebuild. I will use F no secret, this switch. So 242 undeclared identifier arguments. Did you mean I made a mistake? 242 42 ARGUment. I think this is typo. Argument. Okay, I fixed one typo. CLS, we rebuild. Wow, it built, but value is wrong. Okay, it doesn't work. Now let's go up. We know it failed. Okay, it is failed. Now I copy, paste. Instead of doing this, I will use capture by value. Now let's try. We rebuild. CLS, it does not build. If you scroll up, say constant double L-value reference. The problem is that this causes the problem. Now I will simply return 0, okay, to make it build. Now here I will say 0.0. To make it build, we have to check SED, cout, type of ARGU arguments. We need to check the type like this. CPG get type calorie arguments. SED, and there we have to check the type of arguments. Now CLS, it built the, please note this function with capture by value creates constant double reference. So it is constant double reference. We cannot do this because values of arguments cannot be modified. If we build, it does not build at all. No, it doesn't, because the values of arguments are constant. Okay, so I hope you understand why this implementation does not work. I will restore it back. Like this. Okay, then I will disable it. Now copy this, copy, paste. This does not work. Instead, SED tuple arguments. We say ARGs. Now it should work. I will delete. So we have to catch up by value. Okay, not by reference, but by value. We have to capture by value. With this, we can rebuild CLSD. Now our function works correctly. Please note, it does not work. Okay, this is wrong. I will show you CLSD. This is wrong. The result is wrong. Please understand. We are differentiating with respect to z. So internally, we create a function. Then using this function, we differentiate with respect to y. Then using this function, we differentiate with respect to x. So values of z, values of y, values of x are changing in the process. We cannot use L value reference here. We have to use by value capture. With this, it works correctly. Correct. But in this case, this function is copied. So we can fine tune like this. Fun capture by L value reference, then ARGs capture by value. This is perfect. CLSD. Let's test with Clang compiler. I will copy the folder path cd paste Clang ++ std C++20 river thieves.cpp ltbb12 or c.exe, hit enter. CLSC. Please notice, in case of Intel 1 API, the values are correct. In case of Clang compiler, the result is slightly different. We can adjust like this. I will delete 1, 0. Now, Clang compiler, CLSC, Clang compiler gives correct result. Also, Intel compiler gives correct result. Of course, we can try with the GNU compiler too. GNU compiler also works correctly. I will copy, Control Home, paste, Clang ++. See, this is GNU compiler. Of course, Microsoft compiler also works. I will copy the folder path, cd, right click, paste, cl ehsc sed c++20 derivatives.cpp fe and .exe, hit enter. CLSM. Microsoft compiler also works correctly. Control Home, paste it here. It took me 2 years, whole 2 years to implement this algorithm. It can be quite challenging for most people.